Okay, so in this video we're sort of continuing our discussion of linear systems, and we're going to sort of introduce a piece of notation on writing them, which is going to be their matrix form. So as sort of a warm-up for that, I want you guys to sort of refamiliarize yourselves with some of the stuff from linear algebra matrix theory that we've talked about earlier in the class. If you need a refresher on that, I've purposefully left that video still uploaded to Canvas. Should be located under Files. But using that, just sort of go through the following matrix computations as a warm-up. Okay, hopefully you've paused, gone through them. Let's go over the answers. So I'll work through these in a little bit more detail since it is a little bit of a review. So remember that the way we do it is down sort of the rows. Here we go by row, and here we go by columns. And to compute the entries, first thing we're going to do first row, first column. Here we're going to do first row, second column, and so on. So this is going to be 1 times 3 plus 2 times 5. Here this is going to be negative 1 times 3 plus 6 times 5. Here we're going to be 1 times negative 4 plus 2 times 10, and negative 1 by negative 4 plus 6 times 10. So here 10 plus 3 is 13, 30 minus 3 is 27, 20 minus 4 is 16, and 60 plus 4 is 64. So that would be our answer here. Here, 0 times 6 minus 2 times 11, and 5 times 6 plus 10 times 11. So we have negative 22, and 111 plus 30 is 140. So negative 22, 140. Our determinant, remember we do the product of the main diagonal minus the product of the off diagonal. So we have 3 times 10 minus negative 4 times 5, which gives us an answer of 50. All right, for the longer problem, if we look at part A, this should be pretty straightforward. 1, negative 3, and negative 6, 14 is going to be our matrix A. We have x times y. Remember, it's pretty easy. You just sort of make sure they line up. Each variable corresponds to a column. Each equation corresponds to a row. And then you just 1, negative 3, 1, negative 3, negative 6, 14. And what it's equal is the other side, so negative 4, 9. For part B, we need to first compute the determinant. So it's going to be 14 minus negative 6, negative 3 minus 18. So determinant is negative 4. And using that, we get our answer. It's going to be 1 over negative 4, our determinant. And then we swap the main diagonal, so that becomes 14 and a 1. And then we just make the other two entries negative. And so we get as our inverse matrix, if we simplify, move everything inside, we have negative 7 halves, negative 3 halves, negative 3/4, and negative 1/4 as our inverse. Finally, for part C, once we've computed the inverse, we've done sort of the hard part. We just now do one more matrix product. to compute our answer. And we should get our answer of, let's see, so it's going to be positive 14, and then minus 27 halves. So that's going to be a positive 1/2. And for the other one, we're just going to have positive 3 minus 9/4. So 12/4 minus 9/4, 3/4. And so we can write it like that, or we can say x equals 1/2 and y equals 3/4. All right. So that was the warm-up. Now let's talk about the matrix form for ODEs, for linear systems of them. So a lot of times, right, we have in general, we might have something that looks a little bit like this. So, right, x prime, and then we'll have some, some involving x and y. So let's say 2x plus 3y. And y prime, we'll do negative 4x and just y. And you might sort of notice that this is pretty similar to like this linear system problem, right? The setup's pretty similar, right? We have our x's, our y's. Something different on the other side, we have x prime and y prime instead. But that tells us sort of that we can represent this as a matrix equation. Right, so we'll have x prime of t, y prime of t, right? This is what we're equal to. And then we can just do the same thing for our coefficient matrix. So 2, negative 4, and 3 and 1. And then here's our sort of our variables, so x of t and y of t. All right. So this is sort of the main idea. This is really all that this section is about. We'll talk about a little bit more, but we're actually going to introduce a new sort of piece of notation. So this is going to be a very convenient shorthand. So we're going to use a capital X with a bar over it. And then we're either going to explicitly write the t, or sometimes, if it's clear, we won't write it. Will be a vector of variables. So a couple different ways of thinking about this. Of variables, I guess I should be more specific, which are functions of t. So up here, right, we could use our first entry will be x of t, and our second entry will be y of t. Sometimes people might prefer a different way, though. Maybe we'll have an x1 of t and an x2 of t. The other thing we're going to do is talk about the derivative, and that is just the same thing, except we're just going to take the derivative of each entry. Whoops, and I did not mean to put the little bars over that. Sorry if that was confusing. And again, for shorthand, I might drop the t's at some point with this and with the things inside, but I will try to use them at least in the setups just to make it very clear. All right, so given this notation, though, we could rewrite this in one more different way, which is capital X bar prime of t equals okay, 2, 3, negative 4, 1, capital X bar. And this is sort of the form that you're going to be given these sort of problems. Okay. Let's do another example. There's sort of at least one more thing that can get slightly more complicated. Well, kind of two more. So first of all, our coefficients could actually be functions. And we could have things which sort of are unattached to a variable. So let's still see if we can write this in terms of some sort of matrix form. So we could still obviously represent this, the naive way, x prime, y prime, or equals just, vector 5x minus 4 over ty plus t squared 3 over tx plus 8y plus t squared. I mean, we could represent any system of equations with that, but it's not really that interesting. So what we're going to do instead is sort of use something, maybe look at this for a little bit of inspiration. And note, we could also split this up. We could also split these unaffiliated terms sort of over here, which aren't attached to either x or y, and make it their own thing. And now that we sort of look at this part, we can see if we can represent this pretty easily as a matrix. So 5, negative 4 over t, 3 over t, 8 xy plus t squared e to the t, x prime, y prime. So I want to make it clear here, I'm doing a ton of work. I'm just sort of trying to explain step by step what I'm doing. But sort of, if you were given this, really what we would want is something like this. So 5, negative 4 over t, 3 over t, 8 x bar plus t squared e to the t. And just sort of look at this and remember where we sort of came from. So still finding the matrix pretty straightforward. Just make sure to line things up, account for any terms that aren't present by writing a 0. And then if you have these sort of standalone terms, you just write them in a separate vector. I'll do one more, make it a bit quicker this time, and then we will again end this video. I guess before I'll give you an exercise. So write x prime equals 4y plus e to the 3t So 8x minus y plus 6 e to the 7t. And we want to write this as a matrix equation. Okay. So we have these sort of unaffiliated terms, e to the 3t, 6, e to the 7t. We have this thing going on here. So it's important to remember here that we don't have an x term, but so we have, a 0x plus this guy. So this is 0, and then a 4, an 8. Oh, I did not leave enough room. And a -1 times x bar, and this whole thing is equal to the derivative of x bar. All right, and I said I was going to end it here, but I actually want to do one more where we actually solve one, and then we're actually going to write the solution also as a matrix. So writing solutions. So let's go ahead and actually solve one. So x bar prime is equal to 1, 0, 2, 3 times x bar plus e to the t, or actually let's do e to the 2t, e to the -3t. So we're going to solve this and write it in matrix form. So for now, the way we have to solve it is sort of convert it back. So let's go ahead and do that. So x prime of t equals 1 times x plus 0 times y plus e to the 2t, and y prime equals 2x plus 3y plus e to the -3t. Okay, we want to start there because we don't have a y, at least for now. We'll learn some other methods later on, but x prime equals x plus e to the 2t. So x bar minus x equals e to the 2t. Our integrating factor is e to the -t. We integrate both sides. So e to the -tx equals e to the t plus c1, or x equals e to the 2t plus c1 e to the t. Okay. We now have y prime. This is now 2 times e to the 2t plus c1 e to the t plus 3 times y plus e to the negative 3t. Our integrating factor is going to be e to the negative 3t, so e to the negative 3ty equals e to the negative 6t plus 2 e to the t plus 2 c1 e to the negative 2t. The derivative of that, rather, is equal to that. So we integrate and finally solve for y. Oh, plus c2, forgot that. Sorry, what was this? 2e to the 4t minus c1 e to the t plus c2 e to the 3t. All right, so we want to represent this as a matrix or a vector equation. So what we're going to do is we're going to try to line up the parts of the coefficient. So first of all, we're going to have some standalone terms which don't have any coefficients in them. So we can just add those at the very beginning. So x has a e to the 2t, y has a e to the negative 3t divided by negative 6 plus 2 e to the 4t. So those are sort of like standalone terms. But now it's good to line up our coefficients C1. And if possible, also, we're going to pull out it sort of as much as possible. So we'll write it like this first. We don't have a C2 term, so that's just going to be 0. And now what's good to do is try to pull out as much as possible. So we can pull out a C1 e to the t, and then we're left with a 1 and a negative 1. And then here we can pull out a C2 to the t and an e to the 3t and a 0 and a 1. And there's a couple advantages to this. The biggest one is not really clear now, but we're going to sort of end up solving these things in terms of our answers are going to sort of naturally include vectors, which are what we call a tall skinny matrix, 1 by something. So that's one advantage. It's actually going to be easier to write this down than in the standard form. The second thing is, once we have it in this form, it's easier to sort of modify C1. So we can now freely change this vector and still have, or rather we can freely scale it. So if we multiply by -1, like this is also a perfectly valid answer. We can multiply this by 2, still end up with a perfectly valid answer. So on. So it's a little bit easier to get nicer forms for the answer if you have it in that vector form. All right, let's just close. Quick exercise. Should be pretty straightforward. So we're just going to write these, just sort of do some conversions. Or wait. Okay, yeah, so for the first problem, I want you to just take the matrix equation and write it in a standard form. So get rid of all sort of the matrixy mumbo jumbo. And for the second one, do the opposite. All right, so these should be pretty quick problems. For this first one, right, you should have x prime is equal to 2x plus 3y plus e to the t, and y prime is equal to 3x plus 11y plus t. For this one down here, it's sort of good to note we have a plus 0y in here, so we're going to have x bar prime equals 2 over t times 0, 3 over t e to the t x bar, and then we still have this sort of standalone term, so that's going to be plus vector 6t and 0. So those are our two answers there, and I will end it there.